This lecture is about structural properties of Markov decision processes. And this is going to be, I'm not going to finish this lecture today, so probably it continues next time too. So what's the goal here? The goal here is that we study some important properties of value functions of MDPs. So specifically, we talk about something that is known as a Bellman equation, which is very important in kind of all the theory of MDPs RL. And also we talk about something called the Bellman operators. And we talk about some special properties of them called monotonicity and contraction, which are used in both many basic proofs of like why certain things are true, but also used in designing algorithms that are guaranteed to work. So these are kind of important concepts. We focus on discounted tasks. And as I mentioned, we won't finish it today. So we have this concept of return. I just reviewed it. So we have an agent interacting with the world. We get a sequence of state action rewards. So if just we look at the sequence of rewards, then we can define a return of that kind of sequence, which is essentially discounted value of these rewards. So if we look at the definition of return, we see that it has an interesting recursive property. So if we compare g of t and g pi of t at time t and g pi at t plus 1, so at the next time step, we observe that it has this kind of recursive property that basically g of pi can be written as g of pi at time t can be written as the reward that we get at time t plus gamma, the discount factor, times the return at the next time step. So the interpretation is that the return at the current time step is equal to the immediate reward plus the discounted return at the next time step. So this is the basic thing that's much of today's lecture is going to be about. And this is very important because it says that we have this kind of nice recursive properties in discounted MDPs. So a few comments. One is that this return is a random variable. So if we are going to certain state, like state X, and compute the return once, so we get a sequence of rewards, and then we compute the return. And then we go to the same state again in another run, essentially. And then compute the return. These two values would not be the same because they are random in general. Because the MDP is stochastic, policy might be stochastic. But one important thing about this return is that it's the distribution, however, is going to be the same. So it's the same random variable, but not the same value, but it's the same random variable, the same distribution. And it satisfies this equation. Okay, so one question. So when would this, like in different runs, different repeats, when would we get the same return in every run? So anyone is willing to answer?
When the policy is deterministic?
Okay, so if the policy is deterministic,
and the reward is also always stochastic, right? So still random.
Well, maybe you can change it. I mean, what if you make the reward deterministic? So there's no noise in reward. So if it's a function, does it make the return the same in every run or not? I guess you are on the right path. Like you said that if the policy is deterministic and the reward is also deterministic, then the return would be the same in every run. Is it true or not? Okay, so let's see if we have comments. Right, yes. So if transition dynamics is also deterministic, if the policy is deterministic and the reward is deterministic, then the return would be always the same. So if all these three are deterministic, then the whole dynamics would be deterministic, and so we get the same return every time. But in general, they are not. So, okay, so we want to get something that is not random. So we want something that is a fixed function. So what we do is that we take the expectation, the average of g of pi t on conditional state x. So it's a conditional expectation, and then expand the return as we had in the top of previous slide. So let's just see what's happening. Okay, so this is the definition of value function essentially at time t. So essentially what we have is that v of pi at x is conditional expectation of return at time t when we start at state x. So I just expand the definition of return. It would be RT plus gamma times g of t plus 1, again conditioned. So what happens, so I just expand kind of RT, basically write it a bit more explicitly. It would be a random variable that is a function of state xt and also action at, plus the discounted value of return at next time step. So you see here, I'm kind of separating the expectations. So they're the same expectation, but just separated them. Okay, so what we have here, previously we talked about, when we talked about conditional expectation of reward, we had this notation, which is essentially expected immediate reward. So this is RP of x is the expected reward that we get when we are at state x and choose actions according to policy pi, right? Okay. I guess the other term is that, so this whole term, so this is kind of this is the expected conditional expectation of return at time t plus 1. And remember the relation of return and value function. Value function was essentially the conditional expectation of return. So we just write it like this. So we have expectation of v of pi. But here the kind of the thing that you need to pay attention is that the state is not xt equal to x, but the state is xt plus 1. So we condition on being at time t at state x. The agent goes to some other state at time xt plus 1, according to dynamics and policy. And then we compute the value function of it. So you can think of it maybe like this, that if we are like at state x at time t, we may go to some other state at time t plus 1. Oops. And then we observe the value at each of these points. And this is essentially saying that we take expectation of that, like average of it. Okay, is this clear? I guess if we have more heads, I could see more nods. Okay, so let's expand. Okay, so okay, use different color. So this term is clear. We know what it is. This term we kind of need to focus more. What is expectation of value function at xt plus 1, condition on xt being x? Okay, so what does that expectation mean? So it's expected value of v of pi at xt plus 1 when the agent is at state x at time t. It chooses action A according to policy pi and goes to state xt plus 1 according to transition distribution. So it's this process, you have x, choose action according to policy, go to the next state according to dynamics of the MDP. So if you want to write this kind of mathematically, this expectation can be seen as like this, that we start from state, okay, so we start from state x. And then according to policy, we choose action. So according to policy, we choose action. And then this choice of action and state together defines basically what next state we are going through this dynamics transition kernel. So when we have x and we have action, we have this quantity here, and then with some probability d of x, we go to state x prime. And this probability is determined by transition kernel. And then what we do, we compute the average value of value functions that we observe at x prime. So we are at x prime, and we compute v of pi. So this is the whole expectation, conditional expectation that we are doing. But I just wrote it a bit kind of explicitly. So if we have a countable state action space, this would be very similar, but maybe a bit more intuitive. So it would be the case that you're at state x, we determine the policy probability of choosing action A according to policy. And at state x and A, with some probability, we go to x prime and then take average of x primes. Okay, so we combine those things like expansion of that expectation and the first equation that we had. So we get that for any x in state space, v of pi, the left-hand side of the first equation, would be the reward that we get at state x when we are choosing action according to policy pi, plus gamma times this integral of p of dx prime conditional x and a times pi of dA conditional x and v of pi at x prime. So this is called the Bellman equation for a policy pi. And this is kind of one of the most important equations we have here. So what is I think the interpretation should be kind of clear, but it is that basically this is the value of following a policy pi starting from state x. Okay, so I guess I have, yeah, okay, so there's some typo here. So this is the value that we get when we start from state x. We get a reward r pi, and then we follow to the next state and add that reward plus discounted value of expected value of the value function at the next state. So that's kind of the interpretation of it. That was clear from, I guess, the process that I described, how this is kind of generated. So this is essentially, this equation is a kind of recursive equation that relates the value function at current state to the value function at the next state. So if you recall, we also had this notation of p of pi. So this is the induced distribution, transition distribution that is induced by the policy pi. So we can write the Bellman equation also in this form. V of pi of x is reward plus p of pi of dx prime and x. So here you see that policy, that integral over policy is kind of is not here because it is kind of absorbed in the definition of p of pi. So this is a bit more compact notation. And even more compact is this notation, that V of pi is equal to R pi plus gamma times P of pi times V of pi. So I guess I haven't defined what this notation exactly means, but you can imagine what it means. Essentially, it is saying that I define this kernel, take integral of V of pi according to that kernel, and this is defined not just for one x, but for all x's. So this is kind of like a relation between value functions at current state and the value function at the next states for all states. So yeah, so this is kind of the compact form of the Bellman equation, and we are going to see similar things many often because this is kind of more easier to write. Right. Okay, so is there any question? Okay, one other question I have. Can you give me feedback about whether I'm too slow or too fast or just the right speed? Okay, right. I guess I got one right speed. I have 6 comments. Okay. Okay, that's good. So either those who are not satisfied are not commenting, or if that's a kind of sample, unbiased sample from everyone, then you're at the right speed. Okay, that's perfect. Okay, so we can also write the Bellman equation for the action value function, and it would be very similar. So here the difference is that if you recall the action value function, the difference with state value function or value function was that the first action at the first time step, when the agent starts at state X, instead of choosing action according to policy pi, we choose action as in one specific way, like the way that the argument of that action value function specifies. And then after that, at the second time step onward, we are following policy. So that's why we have, so Q pi of X and A is equal to reward of X and A. So this is the expected reward that we get if we choose state, we enter state X and choose action A. So this is the expected reward plus gamma times the integral of this quantity. So this is expected reward at the next time step here, but the first state and action, both of them are already specified by the argument in Q function. So there is no pi here because they are specified. We go to next state X prime and then compute the expectation of V of pi at that next state. So here you see that right-hand side we have V pi, left-hand side is Q pi, right-hand side is V pi. So if you want to both sides to be the same, I mean, this is correct, of course, but if you want both sides to be Q pi, we can just write the definition of, expand the definition of V pi and the relation with Q pi. So V pi was, has this relation with Q pi. So essentially, if at V pi at state X is, we have Q pi at state X, but we choose actions according to policy pi. So if the policy is a distribution, we take just kind of the integral or summation according to action there. So just a question. So suppose the policy is deterministic. So we have pi of X. So this gives us an action. So what would be the relation of V pi and Q pi? So if we want to write Q pi of X, it would be what? Anyone can write in chat or want to talk?
It should just be the argmax of q pi.
If it's argmax.
Oh, I'm sorry, argmax.
Is,
Yeah, so Brian did it right, or I mean, Parveen wrote it right. Yeah, it's the max of the value function q.
Okay, but okay, that's good. So let's go through them. So one is that we have max of over actions of q. So one suggestion was, maybe I just write it. So max over q of, right? The problem with this definition is that it chooses the action chord that maximizes this function. But this is not necessarily the action that policy pi chooses. Policy pi may choose an action which is not the maximizing action. So maybe policy pi always chooses action 1, say, but maximizing action here chooses action 5. So that would not be the case. But there is another choice, another suggestion, which is q of pi of x and pi of x. So this is basically saying that at state x, I choose action according to pi. So it would be pi of x, and then I just compute the value of it. So that's the correct answer here when we have a deterministic policy. Okay, that's good. So I don't write it, the Bellman equation for that case, if it's a deterministic policy, but we also have that, and actually it might be more common to see it throughout this course. Okay, so I guess I'm already mentioned the remark here. Okay, so that's the definition of Bellman equation for a policy pi. So we have it for pi and we have it for q. Sorry, v of pi and q of pi. What about something like Bellman equation for optimal value functions? Do we have similar structure, like recursive structure or not? So that's what I'm going to talk about next. But before that, just let's talk about optimal policy and value function. And we had it in the previous lecture. But so just optimal policy is essentially the best policy. So its value would be higher than any other value. So here I'm kind of, what I'm showing here is that this is x state space, this is v of x. So I'm showing some examples of v of different policies, like policy pi 1, pi 2, and this is pi star, the optimal policy. And you see that all of them are below the optimal value function. So if we find a policy that these curves kind of is the same as the curve that we have here, that would be the optimal policy, and the corresponding value function would be the optimal value function. So essentially, this is like this. So we say that pi star, optimal value function, is the value of v pi when we search in the space of all policies, and we find the one that is maximizing. So here we focus on policies that are stationary and Markov. So policies that do not change, they do not depend on the time step. They're always the same, and they only look at the current states. So I guess there are a few comments. I'm going to talk about that soon. But the reason that, yeah, I think you probably have it. So the question is that, do we have a similar recursive equation, something like Bellman equation, for v of pi star or not? So we don't know that. But the answer is that yes, we do. So that's great. But then when we want to talk about it, we have to be a bit careful, because if we want to be rigorous, we need to go through a few steps of why what we are doing is actually meaningful. It's a bit more trickier compared to having Bellman equation for a policy, fixed policy. I mean, in most cases, people ignore these details and say that this is the Bellman equation for optimal value function. But I mean, this course, because it's going to be a bit more mathematical than basic course, introductory course, we go at least through some of the steps of it. Okay, so what is the argument? So argument is that there exists a unique value, V star value function, sorry, V star, yes, that satisfies the following equation. So we have this equation, which is basically saying that V of pi of x is, we look at all the possible actions and compute this quantity and take the maximum of them. So what is this quantity? This quantity is the reward we get, expected reward that we get at state x and a, plus gamma times expectation of starting from state x and a, going to x prime, and computing this V star of x prime. So this is the Bellman equation, or this is called the Bellman Optimality equation. And this is basically saying that this function, V star, has this recursive property. But what is that V star? Is this the optimal value function or not? So the argument is like this. First, we need to show that this equation has a solution, and the solution is unique. So that's the first part. And usually, I guess, most places, they just said that this is the optimal Bellman optimality equation, and the solution of it is the optimal value function. So the next step, but if we want to be a bit more rigorous, the next step is that we need to show that this V star is indeed the same as the optimal value function, V of pi star, which is the optimal value function when pi is restricted to be within the space of stationary policies. So there is a comment in chat. What situation would the assumption be violated? I'm going to talk about it soon. Just lost one of my screens. So.
Sorry, I also have a question.
Sure, yes.
So my understanding, the value function is basically a vector of scalars over different states. So, or maybe there is a mapping with some parameter theta or something that maps the states to the values. That yeah. So can we always ensure that there is a policy such that for any state, the value at that state is under following that policy is always greater than or equal to all other policies at any state?
Right. So I guess that's a question. We have to prove that that's the case, but so the existence of optimal policy is not trivial. It is imaginable that there is no policy that is always better than all other policies over all states in the state space. But it is true that this is the case.
Okay, thank you. Thank you very
much. Right, okay, so the first part is, I got distracted by some email. So first part is that, well, there is this V star. The second part is that V star and V of pi star are the same. when we restrict pi, the search in pi, to the space of stationary policies. So here I mentioned that this pi is a space of stationary Markov policies. So this is the second step of argument. And then the third part is that, well, why should we care about space of stationary policies? What if we search the space of non-stationary policies? And then it can be shown that for discounted continuing MDPs, for this class of tasks, essentially, or MDPs, then we can always find a stationary policy that is optimal in the space of all possible stationary or non-stationary policies. So basically, the result is that if we solve this Bellman equation, what we find is actually the optimal, the value of it would be the optimal value function for any policy. So this is kind of the idea. I think we are going to, we're going to talk about some parts of it, and some parts of it I'm going to prove later, not today. We'll see how much time we have and how fast or slow we are going. But yeah, I guess we at least proved the uniqueness and this V of pi star. I think we will prove the both of these, part 1 and part 2. Okay, so that was the optimal, the Bellman optimality equation or value function. So we can also define it for action value function. So optimal action value function satisfies this equation, that we are basically saying that optimal value function at state x and a is equal to R of x and a, expected reward at state x, and by choosing action a, times discounted factor of this quantity, which is, what is this quantity? This is the quantity that x and a, we choose state x and a. Again, we go to state x prime according to dynamics. And then we compute this quantity, which is maximum over actions of q star at x prime and a prime. So we take maximization over a prime. So it's a kind of the different a's. We take the maximum of it, and then we take the expectation of the whole thing. So I guess this was the solution that was suggested a few minutes ago, that there was a max of q over actions. So that's true when we talk about optimal value functions, but not for the case of Bellman equation for some policy pi. Okay, is this clear so far? Okay. Okay, so we have defined so we defined what's Bellman equation for a fixed policy, and also we defined Bellman optimality equation. Some questions that you might have is that whether there is only one solution for V pi or Q pi that satisfies the Bellman equation, or maybe there are multiple solutions. Is the question is about the uniqueness of it. And I guess the same question about V star and Q star, the optimal value functions. Is it unique, or there are many functions that satisfy them? So we shall prove that they are unique, but we need some tools before proving them. Maybe one question I have. Okay, so let me go back a few slides for, yeah, this one, say. Q function. Okay, so here, just different color. Just look at this equation. So you see that there are Q pi's on both sides, right? Is this a linear system of equation or a nonlinear system of equation? Just write your answers in chat, maybe. Okay, perfect. This is linear. Why? Because we just have Q one side. The other side is a linear combinations of Qs. Because this integration is essentially linear combination of Q functions. So this goes through a linear combination of things, or we can also say integration or expectation is a linear operator. So everything would stay linear on both sides. So this is in fact a linear system of equation. And I think in one or two lectures, we will see that that's one way to solve these equations. Just think of it as a linear system of equation and solve using a linear solver. But what about this one? Is this linear or not?
No, it's not linear.
Okay, right, it's not linear. Why? What is nonlinearity?
The max operator.
Right, exactly. So this is not a linear system of equation because of the max operator, right? So we have the answers here on the chat. So that's kind of the interesting thing, which means that we can't use a linear solver to solve this equation. So I just wanted you to kind of think about it. Okay, so we talked about the Bellman equation, Bellman optimality equation. Now the question is that how we can get optimal policy from optimal value function. So if you recall in previous lecture, when we had reward, expected reward, immediate reward, for the case of just immediate reward maximization, if we had the R of X and A, we could find the optimal policy by just choosing the action that maximizes the value of R of X and A at that state. So we had something like this that kind of so we had pi star of X was argmax of an action of R of X and A. So it was an immediate reward case. So we want to do the same, but for action value for this continuing task, discounted continuing task. Suppose we know V pi or Q pi. So we can find pi star, and the way we can find it is like this. If we have Q pi, Q star, we just choose the action at state X. We choose the action that maximizes Q star of X and A. So this maximization goes there. And the result of it would be optimal policy at that state. So the other case, if you have V pi, it would be a bit more involved, but it would be similar. So at state X, we compute R of X and A plus gamma times expected value of the optimal value function at the next state. And we add all these things together and find the action that maximizes them. And that would be the optimal value, optimal policy. So one thing that is kind of noticeable here is that the policy, the optimal policy is deterministic. It's a function. For each X, I get one specific action. So I don't need to have any distribution or stochasticity over actions. I can just choose one action. So optimal policy is a deterministic policy. So this is kind of interesting because even though the framework we talked about policy in general as a stochastic policy, for these problems, we can limit our attention to stochastic policies. Sorry, deterministic policies. So this is kind of like interpretation of what is happening based on this equation, how we choose optimal policy. Suppose that agent is at state X. to act optimally, the agent needs to act optimally both at the current time step and also in the future. Because if it's not, so for example, if it's not acting optimal in the future, the agent could act optimal in the future and we get more reward. So we can't make a mistake in the future and still hope that the agent is an optimal agent. Also, we should act optimally at the current time step, because otherwise we could choose a better action at the current step, get more reward at current time, and in long term, we would be a better agent. So it needs to act optimally both now and in the future. Now suppose that the agent, we know that the agent is going to be optimal at the next time step. So we are not worried about that. Somehow it is optimal. This means that when it gets to the, starting from x, it gets to next state x prime, according to this distribution, it follows the optimal policy. Suppose it knows, we know that it knows optimal policy, so it follows the optimal policy. And if it follows the optimal policy, the value that it gets at the next state would be, of course, optimal value at the next state. So it would get v star of x prime. But x prime is random, so the agent can go to different x primes because of this. So what happens is that, so since we do not know where the agent will land in the next time step, the expected performance of acting, we need to think about the expected performance of it. So the expected performance of it is just the expectation of it. So this is the expectation. A criteria, performance criteria, was discounted based on discounted tasks. So the performance would be the reward that we get at this time plus gamma times the expected value that we get at the next time. So the performance criteria would be R of X and A plus gamma times this quantity that we have there. So the expected value at the next time step, which because we assume it is optimal, that's going to be, we have V star here. So what is the choice that the agent has to make? The choice is what action to choose. And we want to find a value function that is as large as possible. So the agent search over all the possible actions and find the one that maximizes this. Which is again, exactly what we have in the, on the top of the slide. So this is kind of like interpretation of what is happening. Yes.
What makes it unique, this solution? So if you're traversing like game tree paths, and then you could have two different paths, right? And with the same reward.
Right. So unique as a policy is unique or value function is unique?
The value function.
So value function, we have to prove that that's the case. But if there are two paths, one of the paths has lower value in expectation than the other one, we cannot choose that lower value path. But in different runs, some trajectory might be lower return than the other one. And that's why we talk about expectation. Like in infinite runs, if you're at that state, how much return we get from there.
So I'm thinking of a concrete case. Let's say like in chess, like you have two different paths for the same move that results in a checkmate. So same sort of like two different trajectories for the same rewards, number of steps, everything's same. So would you have like a unique solution in that case for?
Okay, so I guess in that case, you are talking about uniqueness of policy, because you're saying
right.
what
I see.
In this case, I may have two different choices, two different moves, and both of them are good.
I guess the value function would be unique in that case. In this case, just the policy would be different, but the value function would still be unique.
Exactly. So the policy, so what happens in that case is that you see that here when we take argmax, there is no one action that maximizes that quantity, but two different ones. And the way I wrote it just chooses one of them.
Got it. Thanks.
Okay, so this mapping that selects an action by choosing the maximizers of the value function or action value function is called the greedy policy. So it's a kind of more general concept. So let me just define what it is. So if for a greedy policy for a Q is this function that gets Q, so this is pi of G as greedy. As an input, it gets a Q, some function. So it's not necessarily optimal value function or anything. So any function with the right dimension. Okay, what happened? Okay. Sorry, it gets Q and then computes for state X, computes the argmax of that Q function and returns that argmax. So this is called the greedy policy. And we also can define, we use, oops, there's a mistake here. For V, we can define greedy policy for V. So it's essentially saying that as an input, it gets V and state X and computes this reward plus gamma of next expected value of V at X prime and returns the argmax. And that would be the greedy policy given V. So what we had from previous slide is that if we pass V star or Q star to this greedy policy, or this operation that takes this maximization over actions, the result would be the optimal policy. But here the definition, I guess what is important to remember is that the definition here is for any V, not necessarily V star. So this kind of general concept that this mapping or this function, you give it some V or Q, and it returns, this computes this maximization. And if it happens that you give a V star or Q star, the output of it would be the optimal policy. Okay, so what's the intuition of greedy policy? The intuition is that, okay, so it's some remarks about it maybe. So it's an action selection mechanism that is based on local information. So what do I mean by local? By local, I mean that it doesn't look at what will happen, or doesn't explicitly look at what will happen to the agent in the future by considering all possible choice of actions up to infinity and then computing the return. It just computes, for Q, it just computes some argmax of Q, as in this case. And for V, it just goes one step ahead, like from X goes to X prime, and then computes this quantity. So it's kind of like you can think of it as a one-step expansion in the future. And based on that, it chooses the action. It happens that if we give V star and Q star to it, selected action is going to be the optimal action. If we give some other value function, it's not going to be the optimal action. So why, if we give V star, Q star, it acts optimally? I think the intuition is something like this, that this is because the optimal value function essentially encodes what will happen to the agent in the future if it is acting optimally. So if, for example, for V, I know that at the next time step, I'm going to act optimally. So I just forget about what happens at the next time step, just choose action that at the current time, plus the next time step, I'm going to act optimally in total. So that's a kind of intuition why if we have V star or Q star, we would act optimally. So this is like what I had, I guess, a few slides ago, like that description. Okay, so I guess maybe it's a good time to have a break, a short break. Now is 2:13. Maybe we can start at 2:18, 5 minutes. Okay, perfect. I'll be back. Okay, so let's start again. There was a question that whether for these V and Qs, whether they should be valid value functions for a policy or not, for this to be well defined. No, they don't need to be valid or value function of any specific policy. They just need to be the right dimension. Like for V, it should be of dimension of taking input as state and returning value in real number. And for Q, it should be just anything that takes, any function that takes X and A. Okay, so let's try have a poll. Okay, let's see whether what's the pace of it, whether it's too slow, too fast, or just right. %64% voted so far. Okay, almost there. Just 15 more seconds. Okay, that's good to know. Yeah, okay, I guess it's end poll. So let's see if I can share results. So yeah, 83% think it's just right speed, 10% too slow, 7% too fast. So you can, one solution is, for some slides, it can go a bit faster, so it satisfies some people. But I guess more or less I try to keep the same pace. Okay, so let's talk about another concept that is going to be very important, and that's called the Bellman operators. So Bellman equations can be seen as the fixed point equation of certain operators known as the Bellman operators. So what does it mean? I mean, what's a fixed point? What is an operator? And anything like that. So you will see. So operator mapping is basically what you have seen in many cases, just a fancy name for what I'm going to talk about. So suppose we have a function space, so general space Z, and a mapping from Z to Z. So, and that mapping, we call it L. So this is an operator or mapping that takes an input of a member of space Z and returns another member Z. So just some examples. If Z is real valued number, and this operator is defined as mapping that takes Z and returns Z squared. So that's essentially a function that you all know. So L of 5 would be 25. So now a little bit more fancier operator or mapping is that instead of mapping like a real number, let's map a function to another function. So how do we do it? Suppose Z is space of smooth functions. So functions that you can take derivative of it and everything would be valid. Defined on domain R, so one-dimensional univariate functions that are smooth. So take L to be a mapping that takes Z. Z here is a function, not number. It's a function, and returns the derivative of Z with respect to X, the input of it. So this is a kind of differentiation operator. So L of sine of X, function sine, would be cosine. So the reason I guess I'm talking about operators instead of functions, I mean, I probably could call functions, but is mostly because of this, that operators can operate on more general spaces, like here a space of functions. And Bellman operators that I'm going to talk about are operators that are defined over value functions. So they operate on functions. Okay, so what's the definition? So definition is that this first, the Bellman operator for policy pi. We will later see another Bellman operator called Bellman Optimality operator. So Bellman operator for policy pi is, we have a policy. Here is a stochastic policy, but also could be deterministic. Then the Bellman operator takes, we have two Bellman operators here. One is for V, the other is for Q. So let's see how it works. It takes the first one takes a V and does some operation to it. The operation, the result of that operation is T pi of V. I want to show what is the value of that T pi of V at points at state X. So T pi of V is a function, but the value of it is T pi of V at X is a number. This would be R pi of X plus gamma times expected value of that function V at X prime. And the expectation is according to what we have seen several times already, like the next state distribution, condition on choice of state X, and choosing action according to policy. So this takes many different values. The value at state X is specified here. So that's why I'm kind of showing it here when I define the domain and range of it. T pi of X, T pi is taking a function from space of functions, bounded functions defined in state space X, to space of bounded functions in states over state space X. So the same is true for T pi of Q, with the difference that it takes a Q and returns a Q, right? A modified Q. So how is it? Again, it is like this, that when we evaluate that resulting function here at X and A, it would be reward R X and A plus gamma expectation at the next states. So this is the same as you had seen before when we talked about Bellman equation. But just notice that here, this is not Q pi, and this is not Q pi. So if it was Q pi, it would be exactly Bellman equation. So let me just erase this. So this is the Bellman operator. Let's see the question, I guess. So pi takes as input the state and returns the or actions. Yes, here pi takes as an input X, like here as an input X, and then the result is a distribution over actions. So pi of X, sorry, this should be A. For 1X, it looks like, say, a Gaussian distribution like this. For another X, it might be another one. Or it can be actually concentrated in 1 point. Okay, that's good. So it's good to make sure with these are not becoming confusing later. Yeah, so this is the operator, takes V to another V or Q to another Q. And if its pi is deterministic, we have the same thing, but just we don't have integration over pi. We just here, for choice of action, we just choose action according to pi of X. For Q at the next state, we have the choice of action. This is a typo. This should be so this would be at the next state. Pi would be pi of X prime, but everything else is the same. So this is a Bellman operator if pi is deterministic. So there is a relation, of course, I guess it should be clear, between Bellman equation and Bellman operators. So recall that the Bellman equations was like this. V pi was This is strange. So we have v pi on the left-hand side, v pi on the right-hand side. So this is a Bellman equation. So if you compare it with the Bellman operator, you see that the Bellman operator is essentially saying that if we apply Bellman operator to v pi, the result would be v pi. So Bellman equation written in the notation of Bellman operator would essentially be these two equations. So this is a kind of compact form of the Bellman equations using this notation. Here, just notice that in the definition of Bellman operator, it would work with any v and any q. So it's defined on any functions. But when we compare it with the Bellman equation, we see that if on the left-hand side we choose v pi and the right-hand side we choose v pi, then that would be exactly Bellman equation. Okay. So similarly, we can define the Bellman optimality operators. And as you can guess, we are going to write the Bellman optimality equations using Bellman optimality operators. So it would be the same as before, or very similar. So it takes a v, and when we want to evaluate at x, we compute this maximum over actions of r plus gamma next value of next state. For q, it would be the same, but it would be r of x and a. And here we have, similar to Bellman equation, we have maximum over action at the next state. So this is the Bellman optimality operator. We use often t star. Sometimes people use just t, like t or t star. And when we want to talk about Bellman operator for a specific policy, we just add pi. So both of them are valid. Okay, any questions so far? Okay, so I guess this comparison should be clear. That if we compare them with Bellman optimality, Bellman equation or Bellman optimality equation, we get that the solution of the Bellman, the optimal value function would satisfy these equations. So V star is equal to T star, V star, and Q star is equal to T star, Q star. Again, we haven't proven that there exists such a solution, but assuming it exists, then we can just write it compactly in this form. Okay, so now let's talk about some properties of the Bellman operators. These properties are, basically I'm going to talk about two properties, and I'm going to define what it means. One is that monotonicity of them, and the other is that contraction property. So they are used in many cases. Like one is that when we want to do proofs, we use these properties a lot in order to show that, say, for example, there exists a unique solution to Bellman equation, or Bellman optimality equation. So we use those. But also, when we design algorithms, some of the algorithms are directly or indirectly benefits from these properties. For example, the contraction property, in order to design a procedure that gets us closer to optimal, say, value function. And I think we are going to see it soon. Okay, so the first property is that the Bellman operator is monotonic. So just remember what, okay, so we had similar notation before. We say that two functions v1 and v2. We say v1 is smaller or equal to v2 if for all states x, v1 of x is smaller than v2 of x. So here we have some examples. Like, okay, v1 let's compare V3 and V1. So V3 is always smaller than V1, so that's clear. But if, say, we compare V2 and V1, none of them is smaller than the other one, because there is this region that the ordering would change. So this is just make sure that we know the definition of it. Right. So this is not monotonicity. This is just how we define V1 and V2 and the order relation. Okay, so the monotonicity property is basically this. We say that let's fix a policy pi and choose two functions with the right dimension, like any function, V1 and V2. They are not necessarily value of any policy. And suppose that V1 is smaller than V2. And then we apply T pi to both sides. So we have T pi on the left-hand side, T pi to the right-hand side. So the monotonicity property says that T pi of V1 is going to be smaller or equal to T pi of V2. So what does it mean? Suppose we have, okay, V1 function here and V2 function here. So you see the blue one is smaller than V2, the orange one. Now we apply T star. Okay, so maybe I should say the other part. So for the other part, it's the same. If we apply the Bellman Optimality operator, we have the same relationship. So if V1 is smaller than V2, we apply the T star or T pi to it. It changes, it becomes two different functions, but the order relationship would remain the same. So here I apply T star to V1 to get this kind of dashed line. And to the orange one, I apply T star to get this other dashed line. Since we started from the order relationship that V1 is smaller than V2, after applying them, we still have that T star of V1, this blue dashed line, is smaller than this orange dashed line. So that's basically what we have here. Okay, is this clear what it means? There were questions, let me see. Should the equation say, okay, I guess it's results. The equation say on slide, which one was slide 24? Okay, so the question is that shouldn't the equation say V pi equal to T pi V on slide 24? No, that's both sides, both left-hand side and right-hand side, they should be V pi, because I mean, if you recall from Bellman equation, both sides of Bellman equation, we had V pi. Now, this is essentially the same thing, except that we just use this notation. So when T pi is applied to V pi, so specific function that is the value function for policy pi, the result would be V pi. So that's the intuition. If we apply it to some other thing, like if, say, if V is not equal to V pi, then we cannot say that V pi is equal to V pi, T pi of V. So in general, this is not true. So this is not true. But if it happens to be V pi, then this becomes equality. So that's a kind of interesting thing. Like when both sides are V pi, then that is going to be equality. Otherwise, it wouldn't be equality. And I guess I'm going to talk about a little bit more, but this type of equations called fixed point equations. Okay, so let's try to prove this. It's not complicated. So only prove the claim for T pi, not T star. So just let's start with expanding T pi of, so okay, how should we choose? We have V1 that is smaller than V2. Let's expand T pi of V1. So let's see what it is. For any state x, we have T pi of V1 at state x is R pi x plus gamma P pi. So this kind of more compact notation of dx prime conditional x of V1 at x prime. Because of this assumption that V1 is smaller than V2, this means that for all states it's smaller than V2. So we also can upper bound this V1 of x prime by V2 of x prime, right? And then we just write it again. So it would be R pi plus gamma P pi dx prime of V2 of x prime. But if you look at the definition of it, this would be essentially T pi of V2 evaluated at state x. So this basically, so there is a kind of small mistake here. So when I have smaller inequality here, so it should be. Okay. So we have inequality at these points. So T pi V1 at x is smaller than T pi V2 at x. Because this is true for any x, we can say that T pi V1 is smaller than T pi V2. Is this clear? Okay. So we can prove the same for T star. You will see that the proof in the lecture notes that I'm going to post soon. But the proof is essentially the same. Maybe argument is a little bit, you need one more step in arguments, but essentially the same idea. Okay, now I want to talk about contraction property of the Bellman operators. But before that, I just kind of want to remind you of what contraction is, and contraction mapping, and talk about Banach fixed point theorem. So some of you might have seen it already in your courses. Some of you may not. So let's just review it. So most of the things I'm going to talk about, like I'm going to talk about definition of metric and norm and things like that. These are basic. I mean, these are things that you already know probably how to use, even if you don't know the kind of rigorous definition or formal definition. But so I assume that you know how to use them. Yeah, so let's see. What's a metric? Let's briefly go. Metric or a distance function is, okay, so we have a space Z, some space. So I'm going to give some examples. So it's space, the distance or metric is essentially a function that takes two inputs from that space and returns a number, a real valued number. And it has basic properties of distance as we expect. Like one is that the distance between 2 points, x and y, are always non-zero, non-negative. And if they are 0, it means that x and y are the same. So if there's no distance, they are the same points. And then the distance between x and y is the same as distance between y and x. So x to y, y and x, they're the same distance. And then we have a triangle inequality, which says that the distance between x and y is smaller than x and y is smaller than distance between x and z to y. So if we go in direct path, it would be longer, essentially. Okay, what's the metric space? Metric space is a space that's a set with a distance. So just an example that all of you know is that suppose Z is real valued numbers, real line, and we define distance between X and Y is just absolute value of X minus Y. And then these two define a metric space. So this is something that kind of very familiar. Distance between 2 points is just the distance, X minus 1, the absolute value. The norm is something, similar concept, but a bit different. Norm is essentially what is the size or length of something. And here we focus on linear spaces. I haven't defined linear vector spaces, but this is a vector spaces that you can do linear operations, like you add 2 points and you get a new point. So norm on a linear space is a function that takes one member of that space and returns a number. And it has similar properties. That it's not negative. Like for any point, the norm of any point is always non-negative. So the size of things is always non-zero. Okay, I guess there are some questions. Let's see. Right, okay. Right, okay, so the question is that what's the difference between metric and inner product? And yeah, so I guess the final answer, that you can define norm from an inner product and then you get a metric from the norm is a good answer. But I'm going to talk about at least part of it, not about inner product, but let's get to that point. So norm, essentially distance is distance, norm is the size. So norm is always non-negative. If you multiply X by some scalar number, you get norm of lambda X is absolute value of lambda, like 5, times norm of X. So it's called homogeneity of the norm. And we have triangle inequality. The norm of X plus Y is smaller than norm of X plus norm of Y. And then strictly positive, which means that if norm of something is 0, it means that that point is 0 in that vector space. So I guess one thing that was answering part of the question that was asked is that we can use a norm to define a distance between 2 points by just simply saying that distance between X and Y is the norm of X minus Y, vector X minus Y. So that's the way to define from a norm, you define a metric space. But you can have a metric spaces that are not based on a norm. And I guess the question was about inner product and norm. So, you can use inner product to define a norm, and then from that you can get a metric space. So the spaces that you can define norm based on inner product are called Hilbert space. And we may mention that later during the course, but that's not important now. So some examples of norms that you have seen is that, so for a vector in RD, these like 2, 500, we define LP norm or L infinity norms, like I call LP or L infinity norm this way. LP is technically a bit different, but approximately that's true. So essentially we take xi to the power of p, and then we just sum all the components and then take the pth root of it. And for infinity norm, we just take the absolute value of each dimension and then take the maximum of all dimensions. So that's a norm. Okay, so another norm which might be a newer one is kind of like you can think of an extension of this Supremum norm, infinity norm, but from space RD, vector space, like finite dimensional vector space, to a larger function space, to a kind of more general case. well, not general, but a very different one. So consider space of continuous functions with domain between 0 and 1. So this is the space like X, 1, 0. So the space of continuous functions. And so this space is usually denoted by C with domain 0 and 1. This space of continuous functions plays the role of Z. So here, like in the previous case, Z was like a finite dimensional vector space, RD, but here this is the space of functions. So we define the following norm for a function f in that space. So the norm is called supremum norm or uniform norm, is defined as a supremum norm of f is we take the value of f at x, absolute value of it, and we compute it, in theory, between all values between 0 and 1, and take the maximum of supremum of it. And that would be the definition of it. So given this norm, this space, C between 0 and 1, and supremum norm would be a normed linear space. And we can also define a metric from it by just taking its distance. I mean, this is just one example. Actually, we are going to use this norm. We're going to use this norm to define norms for value functions. So when we have a value function or action value function, we can define their supremum norm via V infinity or Q infinity as just take the absolute value of X and take the supremum, the maximum of it, over the whole state space. Or for action value function, we have it over the whole state action space. Is this clear so far? Let's see. Right, yeah. So there was a comment that inner product induces norm and norm induces metric, yes. Okay, let's define contraction mapping. So contraction mapping is essentially the idea that it's a mapping that makes the distances smaller. Like if you have 2 points, you apply this mapping to it, the distance after applying them becomes smaller. So what is it? Let's more formally, suppose we are in a metric space, Z and D. So D would be the metric. A mapping, so it's an operator, a mapping from that space to another, to the same space, is a contraction mapping, or just simply contraction, if there exist the constants between 0 and 1, but strictly smaller than 1. So it cannot be 1. It can be 0.99, but not 1. Such that for any points in that x1 and x2, sorry, z1 and z2 in that z space, the distance between L of z1 and L of z2 would become smaller than A, that constant, times D of z1 and z2.
Quick question.
Sure.
So if in the Bellman operator, if we're assuming that, so when we say it's contractive, would it be contractive if gamma equals to 1?
No.
So, okay, it has to be, okay, yeah, it makes sense.
Yeah, and that's going to be, we are going to prove that. So, but what you're saying is right. So what we have here is that, okay, so basically what I described here is that if you have 2 points, Z1 and Z2, with a distance of D of Z1 and Z2, I apply L to it. I get LZ1 and LZ2. Their distance would be smaller than A times D of Z1 and Z2. And A is smaller than 1, so the distance become smaller. They become closer. So that's called contraction mapping. Okay, so just some example. Just again, suppose Z is equal to R. The distance is just Z1 minus Z2 absolute value of it, and consider the mapping or function that takes Z and returns A times Z, and A is a real valued number, right? So let's just do calculation to see what happens, like distance between L1. So what we want to do is that we want to prove whether it's contraction or not. We start from after applying the operator. So d of LZ1 and LZ2, we try to write it in terms of d of Z1 and d of Z2. So I just plug in the definition. So it would be distance, the definition of distance shows this. So it would be LZ1, LZ2, definition of L, it would be AZ1, AZ2. So it would be absolute value of A minus Z1 minus Z2. And this is essentially D of Z1 is Z2. And this is the kind of absolute value. So if A, the absolute value of A is smaller than 1, then this is a contraction map. Okay, so why do we care about it? Why do we care about contraction mapping? There are two reasons, essentially. One is that it describes the ability of certain dynamical system. I'm going to describe what dynamical system. And the other one is that it can sometimes be used in order to solve equations, like not only linear equations, but sometimes nonlinear equations. So just talking about stability of dynamical system, I'm starting with a very simple example, just to give you the intuition. Suppose we start from Z0. I'm going to define a dynamical system. I'm saying that Z0 is a member of Z. You can think of Z as a real R, but it can be more general. And then I define the mapping that takes Z and returns A times Z. And A is a real valued number. And now I define the dynamical system in this way. I'm saying that Z of K plus 1 is equal to Z of equal to L applied to Z of K for all K is equal to 1, 0, 1 to infinity. So it's kind of like recursive relation and basically describes a sequence. So what would be the sequence? I'm just writing it. So we start from Z1. We get Z1 equal to AZ0. Z2 is equal to AZ1, which is A squared Z0. So from here. And if I do it many, many times, in general, I get for ZK, it would be A ZK minus 1, which is equal to A to the power of K Z0, right? Okay. So what we have is here, Zk is A to the power of K Z0. We want to see what's the behavior of this sequence, depending on the value of A. Like, does it go to a smaller number, or does it blow up, or it stays the same? So if absolute value of A is smaller than 1, so we have something smaller than 1 to the power of K, so Zk converges to 0. And that's independent of the choice of Z0, as long as it's finite. So we choose Z0 equal to 1000. It would be A to the power of some K times 1000. Eventually, it's going to 0. If A is equal to 1, then Zk is essentially the same as Z0. So it's not changing. So the point that we are converging essentially depends on where we're starting. So it would be Z0. So it's not converging to the same point independent of our initial choice. If A is equal to minus 1, the sequence would oscillate. It would become plus Z0 minus Z0 and so on and so forth. And if it is larger than 1, the sequence diverges, unless, of course, Z0 is equal to 0. So other than that case. So this is interesting, because the only case that this dynamical system converges is when A is smaller than 1. And this is the case that the operator L is being a contraction map. So if it's a contraction map, the dynamics converges. The dynamics that I define this way converges to 0, essentially. So this is kind of the relation between contraction map and stability. Basically, if a map is a contraction, it means that the dynamical system that I define like that would be a stable dynamical system. It would converge. Okay, so that's one. The other reason, I think maybe I finish this like probably 5-6 minutes and then we stop. So the other reason that we use or we are interested about contraction map is because sometimes we can use it to solve equations. And this is something that we actually do in RL later. One of the methods are basically benefiting from this very directly. So let's introduce the concept of contraction map, or sorry, concept of fixed point. So a fixed point is a point, oops, so this should be L. So if you have an operator or mapping L, for any mapping, contraction or not contraction, so it's in general, then a point Z such that L of Z is equal to Z is called the fixed point of L. So this is basically the point that if we apply L, the mapping to it, we get to the same point. So it doesn't change. And if you kind of think about several slides ago when we were talking about Bellman operators, if you recall, we had something like T pi of V pi was equal to V pi. So this is basically saying that this is operator, because it operates on value functions. The point Z that this is satisfied is called the fixed point of L. So here you see that this is going to be based on this definition. It's going to fixed point of the Bellman operator, T pi. So this is kind of the connection, and we are going to use that connection. So this is a definition of fixed point. I'm going to mention it several times probably through the course. We can, and also you can notice that fixed point is related to solution of an equation. How? Suppose you want to solve equation of fz equal to 0. So some equation. I don't know, like, say, for example, cosine of z is equal to z. You want to solve this. You want to find a z that satisfies. We can convert it to fixed point equation by just adding z to both sides. So Lz equal to z if it defines z as a mapping that takes z and converts it or returns f of z plus z. Then if you find a z prime that satisfies this fixed point equation, then we also get f of z prime to 0, equal to 0. So the fixed point of L is the same as the solution of f. So that's why sometimes, not always, we can take an equation and convert it to an operator and then try to solve that fixed point of that operator. Of course, the question is that how we can do it. And this result, this Banach fixed point theorem or contraction mapping theorem, is basically saying several important things. So let's go through it. So it says that let's start with a mapping L from Z to Z. And suppose that mapping is a contraction mapping. So that's the assumption. This is a technical, it's on a metric space, and the metric space should be complete. So we can forget about it now. So it's a metric space with a well-behaved structure. So what does it say is that then there exists a unique Z star in that space Z, such that LZ star is equal to Z star. So this is a fixed point equation, and this is unique. So there is only one Z star that satisfies this fixed point equation. So this is interesting because saying that if you have a mapping that is a contraction mapping, there's only one solution we can get out of it that satisfies the fixed point equation. Also, the way that we can find it, also this theorem suggests a kind of algorithm. It can be found by choosing an arbitrary point in that space. We start from Z0 and then define ZK plus 1 as L times L of ZK. So we get ZK, apply L to get ZK plus 1, and we do it many, many times. The result says that ZK converges to Z star. So if we start this procedure, we apply the Bellman, not the Bellman operator, this operator L repeatedly, we converge to the fixed point equation, or solution of the fixed point equation. So yeah, so basically, I guess probably you're kind of seeing the connection. I'm going to talk about that Bellman operator is an operator which is a contraction. We are going to prove it. And then using this one-off fixed point theorem, we are seeing that, well, the solution of it would be unique because the contraction mapping, the Bellman operator, but we have to prove it. And then we also get an algorithm to find the solution to the Bellman equation. Yeah, I guess that would be. So there's a kind of exercise, you can take a look at it. Next time I'm going to talk about proving Bellman operator is a contraction. Yeah, and also we are going to continue, like this chapter is, the content of these slides just half of the chapter. Okay, that's all. Maybe, I guess we should try to finish now. If there are any questions, I would be happy to answer.